Hello, everyone, and welcome to Saturday Morning Physics at the University of Michigan. I'm Roy Clark, host of this lecture series, along with my faculty colleague, Professor Tim Chuck. Let me first point out that there will be a question and answer session at the end of this presentation, so please email your questions to the speaker to this email address here, physics@umich.edu. And that includes the online audience as well as you folks here in the live audience. I want to now introduce our speaker today, Dr. Carolyn Kuranz, an associate professor in the University of Michigan Department of Nuclear Engineering and Radiological Sciences, one of our most dedicated faculty in the Applied Physics program. Dr. Kuranz is a member of the Fusion Energy Sciences Advisory Committee in the US Department of Energy and has won several important awards, including fellowship in the American Physical Society, the Ted Kennedy Family Faculty Team Excellence Award, and the Early Career Award of the American Astronomical Society Laboratory Astrophysics Division. Dr. Kuranz joined the U of M Nuclear Engineering Department in 2019 as an experimental plasma physicist after earning her doctorate in the applied physics program here at the University of Michigan. And she did her undergraduate work in physics at Bryn Mawr College. Her research interests include high-energy density plasmas and radiation hydrodynamics, and she performs her research using high-power laser facilities around the world, including the National Ignition Facility and the Omega Laser Facility. And a unique aspect of her research is to emulate the conditions in the laboratory that are typical of the most energetic astrophysical processes, in other words, laboratory astrophysics. Please give a warm welcome to Professor Kuranz.
Thank you so much, Roy. Thank you to Roy and Tim for inviting me. I'm really excited to be here. I'm so grateful my friends and family are here, and my colleagues, and even my students. So today we're going to take a bit of a trip to talk about fluid instabilities and where you find them, what their consequences are. And we're going to take some twists and turns to talk about some interesting history and to give some detailed explanations. We'll always make it back to the main path to talk about fluid instabilities, stars, bars, and fusions. So we're going to start with something pretty basic. Let's see. All right, why does a ball roll down a hill instead of up it? You are probably thinking something along the lines of because of gravity, that it has to do with gravity, and that's very true. Gravity is definitely involved, but potential energy is really the key here. So what is potential energy? It's the stored energy due to an object's position relative to some height or zero position. And we can represent this as the PE is the potential energy, is the mass times the acceleration due to gravity times the height or position. or PE equals mgh. Now, for those of you who are unit curious, and when I introduce any sort of parameter in the corner of the screen, I'll have a box with the parameters and their units, if you'd like to know more about that. But for the potential energy, we have, for the example of a ball rolling down a hill, the hill is going to be height h, the mass, or the ball will be some mass m, and it'll be under the acceleration due to gravity, which is g. So nature prefers or tends to a minimum energy state. So in the case of our ball, and again, we have our hill at height h. The top of the hill, we'll say it's a position h sub h. Bottom of the hill is h sub l. The difference between the two is h. So when the ball is at the top of the hill, the potential energy is going to be mg h sub h. And at the bottom of the hill, the potential energy of the ball is going to be mg h sub l. Now, because we know that the top of the hill is higher, or the position is greater, h sub h is greater than h sub l. Pretty straightforward. So this means that the potential energy at the top of the hill is greater than at the bottom of the hill, and therefore the ball rolls down the hill. Relatively simple, so we're going to take these principles and use them throughout the talk today. So you may be thinking, okay, gravity pulls something down, but why does a balloon go up? It'll come down eventually. I did ask permission to leave it here for a while. So okay, so now we're going to talk about buoyancy. Now, when you think of buoyancy, you might think of literally a buoy in the water or a duck on a pond. The definition of buoyancy is a tendency of a body to float or rise when submerged in a fluid. And when I was preparing this talk, I came across this additional definition of buoyancy, the ability to recover quickly from depression or discouragement, resilience, as in the buoyancy of spirit. And I thought that was a really timely definition that we can all probably identify with. Okay, so buoyancy, or the buoyant force, is an upward force exerted on an object in a fluid. And this is represented mathematically as F sub b equals the mass times the acceleration due to gravity, or mg. So if we have a body of fluid, so water in this case, and we have a mass, m, our ball is now, we've taken it from the hill and put it in some water. The buoyant force will be an upward force on that mass. Of course, we'll also have a gravitational force, Fg, that is in the downward direction on the mass as well. All right, so if I have a ball, and I'll do a demonstration in a second, if we have two balls and we submerge them in the water, is that ball going to float or is it going to sink? So I'm going to come over here, and I have these two balls. All right, so I said the important things here are the mass of the ball. So let's take a look at what the masses are, first of the larger ball. And it's 1.82 grams, or sorry, 182 grams. And our second ball, all right, 171, 10 grams, that's a few paper clips difference, so pretty similar masses. I'm going to put them in here, and we're going to see if they float or if they sink. Okay, they're the same mass. One is sinking, one is floating. So what's really important here is the mass density of these spheres. And the density is the mass over the volume. Thank you. And we represent this as the Greek letter rho. That's representing density is m over v. So if we have these two balls over there, the large, ball number 1 was the larger ball, and ball number 2 was the smaller ball. We already measured, they have the same mass. But of course, the larger ball takes up more space. It has a larger volume. And since V1, the volume of the larger ball, is greater than V2, and we know that the masses are the same, the density of the larger ball is actually smaller than the density of the smaller ball. So therefore, the first ball is less dense. That's the one that's floating there. And the second ball is denser, so it sinks. Okay, so from now on, we're actually going to consider energy densities and force densities. So when we talk about the potential energy, and I changed it there, so they're lowercase, then we know it's a force, an energy or force density. So when we have PE equals rho GH is the potential energy density, and FB is the buoyant force density, and it is rho G. All right, so back to our balloon that's up there. If gravity is pulling things down, why does that balloon go up? So here's our balloon. And we often forget that we're actually surrounded by something at all times. We're surrounded by a gas, we're surrounded by air. And the balloons are filled with helium. So the density of air is 1.2 kilograms per meter cubed, and the density of helium is only 0.16 kilograms per meter cubed. So helium is less dense than air. So therefore, the balloon will float to reach a lower potential energy state, and because it is buoyant. All right, so what about if we have one fluid that's on top of another? So in maize, we have a low-density fluid, and in blue, we have a high-density fluid. All right, so when we have the situation where the low-density fluid is on top of the high-density fluid, the low-density fluid is going to float on top, just much like the balloon is floating up there in the rafters, on top of the higher-density fluid. Now, what if we switch them, okay? So we have the high-density fluid on top and the low-density fluid below it. What's going to happen in order to reach the lowest potential energy state is those fluids will want to switch places. The higher-density fluid is going to sink to the bottom, and the low-density fluid is going to rise to the top. So taking a look at these two configurations, what we call them unstable and stable. So in the unstable configuration, you have the high-density fluid on top and the low-density fluid below. But in order to get to the lower potential energy state, they're going to want to switch places in order to get to the stable state. Okay, so it's time for a little demonstration. I have two budding scientists, two lab assistants to help me, Oliver and Helena. All right, so Helena here has water, and Oliver has oil. Want to go ahead and put those in? And we're going to color the water just so you can see it a little better. Unfortunately, blue doesn't show up really well, so we have to use red. All right, so when you're ready, Helena, she's going to pour in our water, and Oliver, go ahead and pour in our oil. All righty. So we did see them when Oliver was pointing. Oh, hang on. Let's put this back so we can all see it nicely. There we go. Okay, thank you both very much for your help. Want to go back and sit down? Thank you. All right, so what we're looking here is we see red on the bottom, that's our water, and we see the oil on top. And as Oliver was pointing in the oil, you saw it did kind of churn and mix up there, but then the oil floated the top. So oil has fat in it, of course, and fat is the lower density. So oil is a lower density than the water. So it'll float on top. And this will actually, even if I shake it up, hopefully I won't make a mess. So even if I shake it up, they will, it might take a little while, but we will begin to see them slowly separate, okay? So even though I tried to mix them, they're going to want to move into a lower potential energy state. And you can see there's some changing at the top as there's some mixing of the fluid. Let me just move it back a little because it's actually clearer on the bottom. There you go. Okay. So we can see it beginning to separate, and it's going to slowly separate over time. If you just want to leave it on that for a second, and I can talk through the next slide. All right, so when I shook it up, it was all the two were mixed up, but then they wanted, again, to reach the lower potential energy state. And so what happens when we have a high-density fluid on top of a low-density fluid, again, they want to switch places. And this is called, and this is due to the Rayleigh-Taylor instability. So that's what the instability we'll be talking about today and its consequences in nature and then also in engineering. And if you're a little more mathematically oriented, the way we look at this is in terms of gradients. So those are just spatial derivatives or changes in space that a parameter has. And if we have a pressure gradient and the acceleration due to gravity creates a pressure gradient so that the pressure is varying in space. And that is pointing here on Earth where we have gravity. That's pointing in the downward direction. And then because of that layered density structure, we also have a density gradient. And in this case, it's pointing in the upward direction. So what happens here is when they're in the opposing direction, when those gradients are in different directions, then you have the Rayleigh-Taylor unstable configuration, and the fluids will essentially switch places to reach that lower potential energy state. Now, in this case, they're pointing up and down, but they can point in left and right, side to side, any different configuration, as long as they are, if they're opposite, they'll be in the unstable configuration, and if they're in the same direction, it will be stable. Okay, so now our fluids have had a time to separate a little bit, and you can see the red water is sinking to the bottom, and then we have the oil, which still looks a little muddy, but you can see it's a little yellow in color, and then you have that center and where you have the oil and water are still kind of together, but you can see that that middle layer is thinning out as the water is sinking to the bottom and the oil is rising to the top. So I think we can, when you switch off the demo. Thank you. All right. Okay, so what happens? We just saw a consequence of that separation of the fluid in the Rayleigh-Taylor unstable configuration. So if we really zoomed in, if we had a really, this is a great camera, but if we had an even higher magnification camera, what we would see at that interface is we would see some structure form and grow, okay? And there's some terminology that we use here called spikes and bubbles. And typically in the fluids community, we refer to the high density fluid as a spike, and the low density fluid as a bubble. I remember it as bubbles float, so that's the lower density fluid. And there's a lot of work going on to study this instability because of some of the consequences that it has, which I'll go into in a moment. Here's a simulation showing one liquid rising and one another liquid sinking. And here's some really amazing data where you've really zoomed in on the structure that's happening at the interface. So time, I'm going to show several cuts. Time is going downwards and also to the right. So in the leftmost image there, that's the initial state of that interface. So you can think of it as the state between the oil and water. And in order to switch places, they need to move through each other. So in this case, you've got that kind of the gray fluid is going to want to rise upward, and then the black here is going to want to sink downward. So we see these structures forming as the fluids move through each other. And as time goes on, we see them, those structures lengthening and developing some complexities, especially at the edges. You start to see these curls, these eddies or vortices forming. That's actually due to another instability called Kelvin-Helmholtz, which I don't have time to get into. And again, we see it lengthening with time. All right, so where do we actually see this instability occur? Okay, so like the title of my talk, we see it in stars, in bars, and coffee shops. and Infusion. Okay, so these three examples is what I'll be talking about for the rest of today. So on the left, we have the Crab Nebula, and this is a supernova remnant, and we see a lot of those tendrils or finger-like structures, and that is believed to be due to fluid instabilities, and I'll talk more about that in detail. And then we have a cappuccino, and we can see some structure developing at that interface there. And then on the very right, we have a simulation of a fusion capsule implosion, and again, there's structure throughout of various sizes throughout the capsule. Now, I think what's truly amazing about this instability is that it occurs at these very, very different length scales, okay? And for a scale, the Earth's diameter is about, I have a little error there. It's about 10 million meters, or 10 to the 7th. And the Crab Nebula, the diameter of the Crab Nebula is 10 to the 20 meters, okay? So many times many Earth diameters. Cappuccino, we're talking something on a centimeter scale, and then these fusion capsule implosions are on the micron scale. And on the smaller end of things, a hair is roughly 100 microns in diameter. So these structures in the fusion capsule are actually smaller than a human hair. But it's the same exact processes, the Rayleigh-Taylor instability, happening in all three of these. All right, so first we're going to focus on what you might see at a coffee shop or a pub. So let's zoom in on that interface here. Okay, so we have our espresso on the bottom, and then our milk is on top of that. And we can see, just like I showed you in some of that data before, we can see the brown espresso is moving upward. You can actually see some vertical structure moving. And then the milk is moving in the downward direction, so it's sinking there. All right, so the density of the espresso is less than the density of milk. It's actually, milk has non-fat solids, so the curds in milk, like Miss Muffet or curds and whey, the curds in the milk are actually higher density, so that will sink to the bottom. So the espresso wants to float on top of the milk. So when poured in this configuration, they will want to switch places. All right, also, this is, we see this effect in bartending. So you might be familiar with a black and tan or a half and half, where you have Guinness is poured on top of a ale, typically a Bass ale. So Guinness has a lower carb content, so it is a lower density than the ale that it sits on top of. And so the Guinness will float on top in order to create this layered structure. Now, does this work for other drinks? Yes, absolutely. Typically, when you see some sort of layered structure in a beverage, it's it's because it's been poured in the Rayleigh-Taylor stable configuration. And you might think, you know what, it's 11 o'clock on a Saturday morning. Why is this woman talking about alcohol so much? It is actually very convenient because a lot of the different mixers and alcohols have different contents of water, sugar, and alcohol in them, and that all affects the density of the fluid. And if you open up a bartender's guide, I took just a few from some that I found online, you'll have, there'll be a list of the densities, right? So here we have, a different liquor, the density of that liquor, and then the color too. So you can make a lot of fun layers there as well. Now, okay, because we have kids here today, is there a non-alcoholic version that you might be able to enjoy? And the answer is yes. So Arnold Palmer wasn't just a golfer, he actually has a beverage named after him as well. And that is where you have iced tea, and on top of the iced tea, iced tea is floating on top of lemonade. Lemonade has sugar in it, which makes it denser than the iced tea. So the iced tea is going to float on top of the lemonade. So a summary of Rayleigh-Taylor effects for bartenders and baristas is that layered beverages must be poured in a RT stable configuration. They cannot be poured in the reverse configuration because as you saw with our demonstration here, they will switch places. to get to the lower potential energy state. You can actually have a lot of fun with this. You can make several layers by varying sugar, alcohol, and fat content as they all affect the density. There is a wrinkle that I'm not going into, and it's called miscibility, which I like to think of it as mixability. And it's essentially whether or not fluids will mix together to form something uniform, or if they'll stay separate. But that's actually a fun activity too, to see if something will become uniform or if the layer will be separated. And of course, whether or not you drink these activities is really up to you. All right, a challenge to all of you is next time you are ordering a layered drink, ask them to pour it in the unstable configuration. I admit I've done this many times. It is fun. I do not recommend just putting a coaster over the beverage and flipping it over, because then it just spills and makes a mess from experience. All right. So our next two examples are in stars and infusion. But wait, aren't stars and fusion systems very different from iced tea and lemonade? Absolutely. They are plasmas. And no, not like the blood plasma. So unfortunately, this isn't really taught a lot in schools. My children, of course, know this, but we're typically taught that there are 3 phases of matter. There's actually more. So let's just quickly go through them. So you're all familiar with a solid that holds its shape. So I have the example of the phase, and then I like to use, water is a great example because we're familiar really with all of its phases. And the solid form of water is, of course, ice, which I have in my drink. We heat ice and it becomes water, it becomes a liquid. So we have the liquid phase, and then you heat water and you get steam, you get a gas, which is something, so liquid no longer has a shape, it takes on the shape of its container. If I were to pour my water bottle on the table, it would just go everywhere, as opposed to the ice, which will stay have a distinct form. And then a gas will just diffuse into a region, has no distinct shape. Okay, so we're taught, typically, most people are familiar with that. If we heat a gas, it goes through a process called ionization and becomes a plasma, okay? So this is sometimes seen in, unfortunately, in the media. They don't like to say plasma sometimes. They'll talk about an ionized gas or heated gas. You'll see a lot of, especially in, well, I'll get into this in a little bit. With the James Webb telescope, there's a lot of amazing pictures coming out. They are all plasmas, but you'll see it talked about as a heated, hot gas, ionized gas. Again, it's really a plasma. All right, so where do we find plasmas? Basically everywhere. So 99% of the observable universe is a plasma. So if you're looking outside at the sky, you see light, it is most likely a plasma. The one caveat is the moon is not a plasma. It's solid, but it actually lights up because there's a reflection either from there's light from the sun, but also there's a reflection from light coming off the Earth as well that you can see parts of the moon. This is an artist's rendition of the observable universe. Again, many, many plasmas throughout the universe. They're not naturally found on Earth, which is most of our lived experience is through what we can see on Earth. But we do see some consequences of, so the northern lights or the aurora borealis has to do with the solar wind interacting with the magnetosphere. And so we can see these beautiful lights in the sky. Also, neon signs have a plasma, a low temperature plasma, certainly not a plasma like we have in the sun or in another star. But plasmas have a lot of technological applications. So plasmas can be used to purify water. My colleague John Foster at U of M does some water purification for cleaning water. Also some sterilization techniques can be, sterilization treatments can be done with plasmas, and there's also some medical advances for healing wounds that you can use plasmas for as well. And plasmas are also heavily used in semiconductor manufacturing, okay? So even though we're not very familiar with plasmas, they're truly, we are actually interacting with them somehow in our everyday life, even if it's just going outside and feeling the heat from the sun. Okay, so plasmas are everywhere in the universe, Very important to technology and also public health. Very cool, but actually they're really hot in temperature. And these still really aren't blood plasmas. That's kind of the most common question I get when I say I'm a plasma physicist. The name plasma from Langmuir, a scientist who coined the term, he identified that plasma is made up of, instead of individual molecules like you'd have in, say, steam, you have kind of like a soup of electrons and protons moving around, and that transport these, and the plasma transports these particles, much like the plasma in our blood transports the red and white blood cells, okay? So that's where the history of the name is, but unfortunately there's a lot of confusion there. And I'm gonna tell you, so for fusion and stars, we're dealing with a specific type of plasma called high energy density plasmas. So these are the hottest, highest pressure, densest plasmas that you'll find. And unlike what the plasmas that you'll see in a neon sign, which is a much lower temperature. Okay, so, all right. So the definition of a high energy density, or HED plasma, is the study of systems with pressures greater than 1 million atmospheres. And to give you an idea of what that is, let's talk a little bit about what pressure is. So pressure is a force applied to an object per unit area. So it's essentially a force per area or an energy density, okay? And so we can write that as F over A, also as F force over area, or E energy over the volume. All right, so I said in high energy density physics, we're at or very often above 1 million atmospheres. So what's an atmosphere of pressure? So right now on Earth at sea level, you're typically at 1 atmosphere of pressure. And you know how if you dive into the deep end of a pool, you can kind of feel it in your ears. And that is literally the weight of the water above you applying pressure to your body. So the deep end of a pool is about 12 feet, 4 meters. Sea level, again, here we're at 1 atmosphere. To get to 2 atmospheres, so just to double the pressure, you have to dive 10 meters underwater, about 30 feet, okay? So that's like multiple pools. So you can't even feel 2 atmospheres of water at the bottom of the deep end of the pool. And we're talking about 1 million of those, okay? So again, a very extreme state is what we're dealing with here. All right, so where do we find these high energy density systems? So here's a plot of temperature and density. There's a lot going on here, but just some context is the surface of the sun is about 6,000 Kelvin, and the density of water is at the 10 to the 0, or is at 1 gram per cc there. And that black line, everything above and to the right of that black line is above this 1 million atmospheres. So you can see there's a huge parameter space, many orders of density in temperature and in many orders of magnitude in temperature and density, where we can explore interesting phenomenon. So you'll see there's the solar core is under these conditions, the Earth's core, brown dwarfs, white dwarfs, also burning ICF, so that's fusion plasma, and I'll talk some more about these systems in detail. So how on Earth are we able to study these types of plasmas that we find throughout the universe? So we can typically use high energy lasers or pulse powered machines. These exist throughout the world. They're very unique facilities. I'll be talking about the National Ignition Facility later in my talk. But we're really fortunate to do this research at the University of Michigan. We have the Zeus laser, which is currently being commissioned, and when it's finished, it'll be the most powerful laser in the world. And we also have the Maze facility as well, a pulse power device. These are both up on North Campus. All right, so back to our main topic here is how does the Rayleigh-Taylor instability affect stars? So again, we have to go back and talk a little bit about stars themselves. Stars are mostly powered by fusion their entire life, okay? So stars, and there are many, many different types of stars, and I'm talking about a specific main sequence star and of a certain mass that follows this life cycle I'm about to tell you about. Stars are mostly made of hydrogen. Essentially, the weight of the star, its mass, presses the hydrogen together until it fuses. I'll talk a little more in detail about fusion reactions later on, but essentially you have hydrogen fusing and it creates helium, it synthesizes helium and releases energy, okay? And this is called fusion or burning. And we feel, and this is the energy source of the sun. This is why we feel heat from the sun, and this is why we have light coming from the sun. All right, so what happens when a star runs out of gas? It certainly can't go to the local station and get more. So if you remember, if it burns through all the hydrogen, but it formed helium in that process. So when it runs out of the hydrogen, it actually constricts. It actually has a small collapse, the temperature rises, and it starts to burn helium. And it actually repeats this process over and over, synthesizing higher Z or higher atomic number elements. And this is how carbon, oxygen, and iron are all synthesized at the center of these massive stars. And what happens in the end is the star looks a bit like an onion, where you have a very dense iron core, and then followed by layers of less density materials all the way out to hydrogen. All right, so there's a really famous quote by astrophysicist Carl Sagan, where he says, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. And this is absolutely true. So iron, for example, we don't make iron on Earth, okay? You know, you find it, you have some ore lines that you can find, but it is made in supernovae. It is made in these massive stars. That's the only place it's synthesized. And then it got here, it's on Earth, and it's in our blood. So it's really amazing to think about, you know, where these different elements came from. All right, so back to our star. So after it goes through these different types of fusion, and you have that layered onion structure, the star actually becomes so massive it can't even support its own weight. So it literally collapses under its own weight. This is called a core collapse. And then, so the mass all concentrates to the center, stagnates, so it essentially gets as small as it possibly can. And then there's a couple pathways after that. One of them is actually called a bounce, where it gets as small as it can, and then you get this rebound, and the star explodes. Okay, so this explosion typically has a huge release of energy, this massive release of energy, and a huge release of light. So astronomers actually would see a star where there wasn't previously a star, and it would be very luminous. So they called it a supernova, from the Latin word meaning new. Essentially, they were saying they see a new bright star. And there's evidence throughout history that people on Earth saw these supernova. There's been a few that you can actually see with the naked eye, and you can actually trace this back to 185 of the Common Era. There's been evidence that Chinese astronomers looked up in the sky and saw a star during the day. And it was for a period of about 8 months they were able to see that. Astronomers have identified that that's very likely a supernova 185. And here on the left is an image from the Chandra telescope. More recently, some of you might remember this. In 1987, there was also a supernova. It was actually the closest supernova in modern times. We actually collected a wealth of data from it. And here's an image from the Hubble Space Telescope. And when I say closest, it was only 168,000 light years away. So that means that the light from the supernova took 168,000 years to get to Earth, or that by the time we saw it, it had happened 168,000 years ago. And that was considered very close. That gives you an idea of just how huge the universe is. All right, so there's a lot of excitement about the James Webb Telescope that you've probably seen in the news. amazing images. It's such an exciting time. Here's an example of the Southern Ring Nebula. And again, on the right side here, we see this filamentary structure, which again could be from the Rayleigh-Taylor instability. So we're seeing some really amazing things, and even though these things happened so long ago and they're so old, we're really learning a lot of new things about them. So when the Hubble first started sending images, it was a really exciting time for science, and now again with James Webb, we're seeing this amazing, especially these structures that we're seeing. So definitely keep an eye out for what's happening there. All right, so back to Rayleigh-Taylor. All right, so how does Rayleigh-Taylor affect stars? So let's go back to our onion star, if you will, and you might think, well, this looks really different from a black and tan. How can this be Rayleigh-Taylor unstable? So let's just look at a little slice of the star. And we actually, if we cut that out, we see, again, this layered density structure, where at the bottom here we have the high density from the core, so the iron, and then layers of lower density materials. Again, this sets up a pressure gradient. And that explosion I told you about, that's accelerating the material outward. So on Earth, we don't think about it, but because it's always happening, but we are under the acceleration, under the effects of the acceleration due to gravity. But there are other ways to accelerate. Certainly in a car, if you brake or speed up, those are types of acceleration or deceleration, right? And so the explosion provides this acceleration, which creates that pressure gradient I told you about. So again, we have these opposing pressure and density gradients, an acceleration of a layer density structure. So these are also Rayleigh-Taylor unstable. And there are, as I mentioned earlier, a lot of the structure that we see in the stars is believed to be due to the Rayleigh-Taylor instability. This is Cassiopeia A, a supernova that exploded in 1680. Again, this is 10 light years across, so really, really massive structures. And there's a lot of work to be done to understand the development, the evolution of these structures. So here's a simulation from the Max Planck Institute for Astrophysics of a supernova explosion. It looks kind of like a peach, and it's actually a star, but they've cut out a section, a peach slice, if you will, in order to look at that internal structure, because we can't really look into a supernova while it's happening, right? If the closest one happened 168,000 years ago, we really can't investigate it. We just see kind of the end product. So again, you have a dense core, and you see these structures developing and being ejected outward as we look inside. And if we go later in time, further development of those structures, pushing those dense materials outward, until finally you can see it gets to that outer surface and affects the overall structure of the supernova. So a little summary of the effects of the Rayleigh-Taylor in supernova explosions. Supernova create heavy elements that are necessary for life. So, iron and calcium are all created inside of stars. Supernova explosions are Rayleigh-Taylor unstable due to the layered density structure and the acceleration due to the explosion. And the Rayleigh-Taylor instability ejects these heavy elements into the universe. So finally, for the last part of my talk, what about fusion? Is it also Rayleigh-Taylor unstable? So let's talk a little detail about fusion. So we have two elements. In maize, we have the proton. In blue, we have the neutron. Protons is a particle with a positive charge. A neutron is a neutral charge, but it's roughly, for these purposes, they're roughly about the same mass. So if we deal with the simplest element, hydrogen, hydrogen is one proton, one electron. We're mainly looking at mass here, so we're not going to really consider the electron because it's because the protons are so massive. Hydrogen has two stable isotopes, so they're called deuterium and tritium. Deuterium is a proton with one neutron, so it's roughly twice the mass of hydrogen, and tritium is one proton and two neutrons, or roughly 3 times the mass of a proton. Where do you find these elements? Deuterium is naturally abundant in our oceans. So deuterium is sometimes called heavy water. So water, obviously H2O, and sometimes it's, I guess, well, it wouldn't be D2O, it's like 2H2O, but it's a deuteron with 2 deuterons with an oxygen, it's a molecule with 2 deuterons and an oxygen. And so deuterium and tritium, I'll go through the reaction in a minute, but it is the fuel for fusion. So just 1 gallon of seawater can produce as much energy as 300 gallons of gasoline. So just 1 milk carton full of seawater. And there are 352 quintillion gallons of seawater in the ocean. I had to look up what a quintillion was. So just a really just extreme amount of deuterium is just present in nature. Tritium is much, much rarer. However, that tritium is actually a byproduct of fusion. So fusion it can get to a point where it produces its own energy its own fuel as a byproduct. So for a typical deuterium-tritium fusion reaction, we have a deuteron and a triton. They are confined together, and there are many different mechanisms or ways that you can confine these. I'm going to focus on one type called inertial confinement, but essentially they're compressed together until they fuse, and so you have two particles you press together of a certain mass, right? So here we have 3 neutrons and 2 protons. And they create the byproducts of two new particles with a difference in mass. And that mass difference, while very small, is released as energy, right? And this actually uses Einstein's famous equation, E equals mc squared, where m is the mass difference in this reaction. So mass itself holds a huge amount of energy that we can harness through fusion. So I'll focus specifically, I said, on inertial confinement fusion, a type of fusion research that's done at the National Ignition Facility. So this is in the Bay Area in California. It's the world's most energetic laser. This is a schematic. It's about 3 football fields in size. But the fuel that they use is about 1 millimeter in size. So we have these very tiny fuel pellets that we use. The fuel pellet, I'll talk about it in detail, but is essentially some sort of deuterium-tritium mix as the fuel, and it's encased in a small plastic capsule. It's about 1 millimeter in size. And in August of 2021, so just last year, the NIF experiments exceeded the Lawson criterion. So this is the scientifically accepted threshold for fusion. I'm not going to say much about this, but I would just encourage you to look out for some exciting announcements, perhaps next week. Maybe put a Google alert on for the National Ignition Facility. It's a really exciting time in this field. All right, so NIF is actually an engine for the future. You may have seen it. This is the movie Star Trek Into Darkness. And actually they filmed it at the National Ignition Facility while it was under construction. And anytime you see Scotty and he's in the engine room, behind him is the target chamber. So that's what we're seeing here. And they actually had that as the engine for the ship. So a brief overview of inertial confinement fusion is that you have this capsule. So you have this deuterium-tritium fuel encased in a plastic shell, and they use either lasers or X-rays to heat that surface of that capsule. So what happens when you heat that plastic is it ablates away, so it moves very fast in the opposite direction. And we know from Newton and from Hamilton that every action has an equal and opposite reaction. So if something moving very fast in the outward direction, you get the same reaction in the opposite direction. This is called the rocket effect. So as you have material ablating outward, you also have a shock wave moving inward. And ideally, we get to a peak compression of 20 times the density of lead and greater than 100 million Kelvin. So to think about the context, if you go to the dentist or get an X-ray, they put on that iron apron to protect you. So we're talking, and it's really heavy. So this is 20 times as dense as iron. And 100 million Kelvin, the surface of the sun is only 6,000 Kelvin. So we're talking about actually hotter than the surface of the sun. And hopefully we get to burn or a self-sustained thermonuclear fusion reaction. And again, this might sound familiar to you. If you've watched Spider-Man 2, when Dr. Otto Octavius was introduced, Doc Ock, he built this machinery where he inserted a small pellet of tritium and then symmetrically irradiated it with lasers and until they formed a fusion reaction. So I was really impressed by what they got correct in this. Obviously, there's a lack of safety protocol, or Doc Ock he is wearing glasses, but the bystanders are not. But of course, this is all done in vacuum. And of course, then there's a big departure from reality as he basically makes a sun. Things really go awry. Spider-Man gets involved. Things get really bad, and then the whole thing explodes. So this definitely isn't reality. This is definitely departure. But it is neat to see this in everyday science. So let's take a look at that capsule and how it relates to the Rayleigh-Taylor instability. So if you remember our capsule, we have, again, a plastic shell on the outside, and then we have a layer of deuterium-tritium ice, so solid deuterium-tritium, and then filled with a gas. Again, let's just look at a little slice of that, and it's actually and so we have this layered density structure again. And it's actually, it creates this density gradient from low density to high density. And then that compression, that inward compression, again, is an acceleration. This is actually essentially the opposite of the supernova, where we have it exploding outward. This, we're trying to compress it inward. So we have those opposing pressure and density gradients, and we get the Rayleigh-Taylor instability. And this is actually a very negative consequence for fusion, because when you get that dense, cold material into the fuel layer, it actually reduces the fusion yield or stymies the reaction. This has been known about for a long time. Here's some experiments from 1997 where they're viewing essentially a cylinder that they're compressing, but we can see that kind of wrinkle around that, the feature, those fingers. And that is mixing due to that's the layers mixing due to the Rayleigh-Taylor instability. More recently, this is a simulation done where they see these structures of various sizes. Again, that affects the overall yield of the implosion. Just the fact that they were able to do these simulations is pretty amazing. They did it on a very large number with computational zones on 6,000 processors. Even with that, it took months to complete. All right, so who is working on fusion? There's actually a really interesting Ann Arbor history here related to fusion. So Kip Siegel was a professor of electrical engineering at the University of Michigan, and he started KMS Fusion in 1967. And it was the first private fusion company to work on the ICF method. And it stayed open till about the 90s when it shut down, but we still see some remnants of it around. So the Sleep Disorders building is at 700 KMS Place. That was the location of KMS Fusion. So that's down by the airport. There's a U-Haul right next to it on KMS Plaza. So that was the location of the first privately owned fusion company. Now, who's working on fusion today? Well, it would seem just about everybody. So there's a lot of private companies working on fusion. Some have been working for decades, and some have just started recently. So as I mentioned, there's different mechanisms to create a fusion reactor. So these are not all ICF-based companies. There's some different methods as well. There's been some exciting developments in other areas as well, and not just with the recent results from the National Ignition Facility. But it's a very exciting time, indeed. So there's a joke that I'll just address, is that fusion's always 20 years away. So today I will not be giving a timeline for when fusion will happen, but I think part of this is that fusion is really hard, and there's a lot of scientific and technological challenges to fusion and that we haven't figured out yet. And the whole 20 years, sometimes it's 50 years, is I think it's hard for us to envision as humans what we can do beyond our own lifetimes. So if we look at some other achievements that really changed society and humanity. If we go back to 1903, really not that long ago when you think about it, was the first human-powered flight by the Wright brothers. And less than 20 years later was the first international commercial flight from London to Paris. So an entire industry was created and that began flying passengers to different countries. And then again, less than 50 years later, we went to the moon, okay? So it's just a pretty amazing timeline, right? 70 years between the first human flight and putting a man on the moon. That's really a short amount of time in the history of humankind, and just an amazing feat. And for the younger folks in the audience, we did this without an iPhone. We did it without a computer. When they did make computers, they were the size of a room, okay? And then we made it small enough to put in our pocket. So truly, I think human beings can do whatever they want to. If they put their time, effort, and energy in it, we can do some really amazing, amazing things. And I don't really know what the Wright brothers were thinking about that day, but I'm pretty sure they weren't thinking, okay, first step, human power flight. Next step, we're going to Mars. So I think that it's hard when you're in it and doing this work to kind of envision what the possibility could be. I can't imagine they even thought about people landing on the moon when they did it, even though it happened only 70 years later. But there's a lot of amazing things that we're able to do, and there is some exploratory work about going to Mars and what we would do. And I think there's a lot of unknowns about going to Mars. There's scientific and technological developments that need to happen. But if we put the time, energy, and resources behind it, I'm confident we can go to Mars if that's what we decide to do. And actually, on the way over here, I heard on the news that it's 50 years ago today that the last human walked on the moon. And as you may have heard, there is a kind of reinvigoration about sending humankind to the moon. So I think it is. I'm very excited for what we are able to accomplish. So some conclusions about fusion. This is a societal grand challenge. As I mentioned, the fusion fuel can produce enormous amounts of energy with readily available fuel. And a lot has been learned, and certainly there's a lot of things to be done before we can count on fusion power. There's still a lot of science that we don't understand and need to work through. And many of the ICF designs are inherently unstable, which affects the yield and the energy output of that reaction. So there's a lot of the work that I do in my regular job is to understand the fundamentals of the Rayleigh-Taylor instability under these type of conditions. And some different mechanisms are trying to mitigate the instability or to implode it quickly enough so the instability doesn't reduce the overall yield. So again, that's a very active area of research. And I think this is a really exciting time for fusion, and you should definitely be looking out on the news to see what's to come. So overall, I hope you learned a little bit about fluid instabilities and their consequences. And some key takeaways is the Rayleigh-Taylor instability occurs due to buoyancy, and RT stable configurations are in their lowest potential energy state. Plasmas are absolutely everywhere. Fusion energy should be aggressively pursued. And just because it's Saturday doesn't mean you're not going to have some homework today. So I definitely challenge you to go and order a layered drink in an RT unstable configuration. Have a little fun. I also encourage you to learn more about fusion energy at usfusionenergy.org. And also check out the new James Webb Space Telescope images. Some really amazing images has come out, but there's a lot more that can be done. And thank you very much for your time.
thank you, Carolyn, for that wonderful talk and overview and bringing us up to date on the latest. There are many interesting questions that have arrived, and I'm sure you'll be interested to answer those. I want to start with the first question. I must not miss this one because it's from someone called Carolyn Kuranz, who has announced herself as a baker and wants to know what aspects of physics are important in baking. So thank you for that question.
Hi, Karen. That's my mom. Thank you for joining. Oh my gosh, actually physics is really important in baking overall. Certainly, and I've watched Karen bake amazing things over the years, but certainly when you're dealing, I mean, just if we think about the density, right? You want to get those air bubbles in the bread, and how you get at the right density so it's, that exact texture that you want and enjoy, and those bubbles forming in your yeast, right? There's a lot of chemistry there as well. So really physics is everywhere as well, and getting your recipes right is really going to be key to get the flavors and textures that you want.
Thank you. And we always say, physics is everywhere and everything.
Yep.
Another question that came in is on the demo that you did with the oil and the water.
Yeah.
And there are three parts to this question. And kind of overall, this is a really interesting question because related to the extraction of oil, as oil becomes less abundant and harder to get, then methods like fracking are used and water injection into porous rock and so on. So the first question is, why doesn't the color of the oil get into the red color of the water get into the oil?
Yeah, that's a great question. So that has to do, again, with the miscibility of these fluids, and that there are, because of the features of the oil, I guess, there's essentially barriers that prevent that from getting into the food coloring or even the water into the oil. And I think we've all, gotten some oil on our hands at home, and you really, only Dawn dish soap gets it off. So you really need to kind of cut that oil. So there's actually, there's a lot of details about fluids that I didn't even go into, but a lot of how they interact with other materials and other fluids is actually extraordinarily complex.
Mm-hmm. Okay. Then another question related to that is, would the separation of oil and water work if bubbles or droplets didn't form?
Would the separation work? Yes, it would. So so we do, and you can come up and look at this later, and I think this is what they're getting to, is that you do have this kind of droplet and bubble structure in there, but they are because of their overall miscibility, they are always going to stay separate unless you do something to change the fluid itself. So something if it undergoes some sort of phase change, if you heat it, if you add other chemicals, other materials to it, and do some sort of, but then it essentially won't be in the same state it is in, that they won't mix. Again, if you've made salad dressing, oil and vinegar don't mix, but sometimes if you shake it really hard or you use some sort of like one of those immersion blenders things, but then you're actually changing the state, and it's no longer oil and water, it's something different.
And then the person who asked this question noticed that there looks like an additional layer on top of, they suggested, water.
It is hard to see, and I do encourage you to come down. That's a great question. I do wonder if that is maybe some sort of contaminant in the oil that has separated out as well, but I'm not 100% sure what that is. That's a good question.
Okay, great. So So what happens in the case where you have a fluid that is being accelerated in some way? And this is a question related to the way that a centrifuge might work in uranium enrichment, for example. So,
oh, that's interesting.
So how does that go?
Okay, so sure. I mean, I'm not sure of some of the details here, but certainly in a centrifuge, you'll also have an acceleration, right? So we're very familiar with acceleration due to gravity, but we saw in the star and fusion examples, you can have acceleration in a lot of other ways as well. So either explosions, compressions. Accelerations are just a change in velocity over the change in time, right? So there's a lot of ways to get those different accelerations. If acceleration will certainly cause something to a liquid to move, but if you say have multiple fluids in a centrifuge and you're accelerating them in this due to the centrifuge, then there could be separation or Rayleigh-Taylor instability. It comes to mind if you could take your blood taken and you put it in the thing and it spins it around, that's an acceleration too, and they use that to separate elements out of your blood as well.
Good, and then I really like this question. Why do gases mix and not separate, even though they may be of different densities?
Oh, that's a great question. Right, so gas tends to take, this is challenging to describe. I guess gas has no distinct shape or containment. However, you can do gas and look at Rayleigh-Taylor instability. So gas can often behave as a fluid. It can have the same behaviors in a fluid and also actually be separate from something. So you can't, there's not a lot of gases we can actually see and look at this evidence, but there are experiments that look at a gas layer and a fluid layer and how they mix as well. So there's a lot of variations there as well, depending, again, on what sort of gases you use, but also how we visualize these things. A lot of times we can't really see, and especially on the time scales of salad dressings or oil and water, you can't necessarily see some of that structure and that mixing that's happening, or at such a small scale.
I'll add a little bit to that in terms of what happens when you cool a gas, then that fractionation has a different effect.
Absolutely. So I didn't really talk much about temperatures here, but that actually gets even more complicated when you have fluids of different temperatures, and then you have what's called a temperature gradient, and you can get actually something rising due to convection. So that's actually a completely separate process, but actually can induce fluid or gas motion as well, and also change the densities of these systems. So yes, they can get very complex quickly.
So another interesting question. Surface tension, is that important for the Rayleigh-Taylor instability? And how does that play a role?
Absolutely. So I kind of said that kind of the bare minimum you need to get Rayleigh-Taylor instabilities, but there's a lot of things that affect the growth and the development of the structure. So surface tension was mentioned. That actually minimizes the fluid growth. A lot of times in plasmas, so in stars and stars and fusion systems, you don't need, surface tension does not have a large effect. Something else that has a big effect is also viscosity. So that's kind of like the thickness of the fluid. So oil tends to be very viscous, or think maple syrup. That also will mitigate the Rayleigh-Taylor instability. So in kind of everyday life, something like surface tension or viscosity is definitely going to have an effect, but those effects are minimal when we go into stellar plasmas or infusion plasmas as well.
And the second part to that question was, how does soap help when we have grease on our hands and oil?
That's a great question. I actually don't know the answer to that, why the soap is able to cut through it. Again, because that's not like my active area of research. I just know if you have greasy hands, you need to get the Dawn out. So.
Yeah, in case anyone wants to follow up on that, the word surfactant is the key word, and you can kind of go and look for that on Google. All right, so now there are a few questions on the more higher energy kind of processes. One of them is to do with how fusion works to produce orders of magnitude more energy, and how do we not cook ourselves? I'm not really sure what that.
Yeah. How do we not do what Doc Ock did and blow up our whole lab?
Yeah, go ahead.
So I will say fusion is very challenging, and we do want to create, so when we have these very small pellets of DT fuel, we're not going to get a huge amount of output in those type of experiments. Certainly if we had, a power plant's worth of fuel, that would be a different scenario. But if we were going to go to a power plant, we would definitely, there are controls that you would want to have to stymie the reaction if needed. Fortunately, and as I mentioned, that you can get into the case where you burn up that fuel and actually can generate additional fuel. You can synthesize additional, especially tritium or deuterium, that can also burn. Fortunately, fusion is so hard to do, it's actually really easy to stop doing. So, a simple just cooling down of the fuel will stop the reaction pretty simply. But yes, the experiments that I talked about in the laboratory, it's such a small amount that even if we do get a self-sustaining burning reaction, it'll very quickly, in nanoseconds, really, less than a microsecond for sure, burn through all that fuel. And we do see a neutron source that's what we detect. We see the neutrons coming out. But even that is pretty minimal in the scope of things.
And I remember when these very high power lasers started to be part of the public consciousness, people worried about creating mini black holes and whether they would suck everything in.
Right. So I think a big thing to remember is that when you do form a black hole, that there's more mass involved than the Earth, right? So they're collapsing that to a very small point. So we don't even have enough material if we use the entire Earth to create a black hole. So definitely not doing it in the lab.
All right, so here's a question about the kind of geological aspects of the RT instability. Inside the Earth, there are giant plumes of magma. Is this an example of RT instability?
That's a good question. I'm definitely not a geophysicist, but I would think the magma is very hot, and it's likely rising due to convection. So it's likely rising because there's this temperature gradient, and you've got very hot gases. So I would say it's more to do with that than this buoyancy or due to acceleration.
So we're kind of moving now to something that may be related, maybe not, but how could RT, Rayleigh-Taylor instability, affect dark matter?
Oh gosh, that's a good question. Yeah, I don't know. I'm not as familiar with dark matter, right? So this is the idea that there's, if you kind of are able to theorize how much matter is in the universe and then if we kind of see what we can observe, this observable matter, which is essentially plasma, as I mentioned, there's a lot missing, and that we think that that's called dark matter, so matter that we're not seeing, that's not emitting light. So that's a really great question. Again, we'd have to take it back to like, what are the specific densities? What kind of matter is that? And look at different types of acceleration. So there's definitely in astrophysics, there's a lot of density gradients out there, and there's a lot of pressure gradients due to explosions and different interactions of materials. So definitely it could have an effect, but I'm not familiar with the specifics.
Yeah, so we'll have to have that question asked again in a few years
Yeah,
as we
exactly.
understand more about dark matter. A question about the status of magnetic confinement. I mean, you did say there'll be a very important announcement, and I assume that's to do with the magnetic confinement or inertial or with the pellets.
Right, so that's a great question. So Roy just brought up magnetic confinement fusion. So that is a different mechanism for confining this fuel. As the name suggests, it's using magnetic fields to confine deuterium and tritium. So everything I talked today is called inertial confinement. It's just a different method, but seeking to do the same, fusing this deuterium and tritium. So if you're familiar, you've heard about ITER or Spheromax or Tokamak, that is all in the magnetic confinement regime. They've actually have made really incredible advances recently in the magnetic confinement area. So there were some science articles coming out of Europe on the JET machine where they were able to produce a very significant yield. They've also made some amazing advancements in magnet technology as well. But so that's just a different aspect of the fusion community. Yeah.
Okay, great. I want to finish up the question session with your kind of insights into how you got into science and what kind of set you going along the wonderful path that you've taken so far, and could you give us a little bit of insight on that?
Yeah, I'd be happy to. So I just really fell in love with science at a really young age. I remember I was in fifth grade and just had a science teacher, and I loved just learning about how everything worked, and I was just so curious about it. So it really became a joy, and I would say from that age on, I knew I wanted to be a scientist, and I wasn't really sure what kind of science I wanted to study, but I'd taken different courses in science throughout school. I did actually a big influence in my life as I did go to college to Bryn Mawr College, where my friend Emma also went to. And it's an all-women's college. I was a really shy kid. I was the youngest, so I was the third daughter. And I just really quiet. And going into a women's college really encouraged me and gave me a lot of confidence in science. So it was really influential in my life. I had actually thought I wanted to be a biology major, but I had gotten an AP credit for biology, so I didn't have to take introbiology. But all biology majors have to take physics. So my first semester of physics, my first semester of college, I took a physics course and just loved it. And that semester on, I said, I want to get my PhD. I want to be a physicist. I want to understand how everything works and study different things. And I have a Post-it note. I went through the whole semester, and I just aced the final, and my professor, Neil Abram, put a Post-it note on my final and said, come talk to me about majoring in physics. I still have it today, but that was definitely a point in my life when I thought, okay, this is what I'm going to do. So I was definitely, had a lot of interest, but then there were really key people that encouraged me along the way and had a lot of positive experiences. And then I do have to say, is that then I came to University of Michigan into the applied physics program. So obviously, Physics does not have a lot of diversity, not a lot of women for sure. So it was very shocking to go from an all-women's college into a large R1 university. I think I was the only woman in my incoming class, but again, just like the support of being at an all-women's college, coming to the applied physics program, which Roy has been so integral as being a part of, again, was a place that I found amazing support for a lot of the struggles that you go through, and it's just such an amazing program, which is why I'm so happy to still be a part of it. Science involves a lot of failure. And even some of those like really exciting things with the Wright brothers, they failed a lot before they did that. We had a lot of failures in the, in going to the moon as well. And but I think that the important part of science is to keep going when you have a misstep or a failure, to have buoyancy of spirit, perhaps, and so doing that in a supportive environment is really important.
And do you have any advice on, say, a high schooler who is thinking about a career in science? How do they get involved? What's a good way to get involved?
That's a great question. So there's definitely a lot of, there's a lot of resources out there, asking a lot of questions, contacting people. People reach out to me all the time with questions about science, about physics, about fusion, about plasmas. They might not get back to you, but keep trying, because I think you can definitely find someone. There's a lot of summer camps out there. The National Science Foundation does a lot of work to provide opportunities for people. So find these opportunities, searching summer camps, internships, asking questions, exploring, reading, all of these things. I think, be curious. That's the most important thing.
All right, terrific. Now, I said there were a lot of questions. There's one more came in just now. So let's finish up with that. How do you use the James Webb Telescope images for your work?
That's a great question. So I have a colleague, an astrophysicist out of Rice, that has some James Webb time on the James Webb, and a lot of the information coming out of James Webb is very new, and there's a lot yet to come. So the idea is kind of connecting people of different expertise. And this is what I love about science, is collaborating with other people who are related to, but also do something slightly different from me, so that we can kind of, be greater than our individual selves. So I have some colleagues that I work with, asking them, questions about their work, seeing if we can make connections to mine. And there's a lot of things that we can study using James Webb. However, all of these things we're looking at, like I said, are very far away. And while there doesn't seem to be a lot of stuff between things, because there's so much space, there's actually a lot in the way, a lot of dust. And we can't see into things. We can't order up specific things. Let's look at the supernova explosion. So what I can do in the lab is look at things in a controlled setting and look at really specific processes. So again, I connect with people who have expertise doing observational astronomy to find out what the key dynamics they're looking at, and then I can study it in the laboratory as well.
Yeah, this James Webb Telescope you've got to keep your eyes on that. It's
It's really
a revolutionary instrument, not just another telescope, but with capabilities that change our view of the universe. And
absolutely
watch that space.
Yeah.
So let me conclude our event today by thanking Dr. Kuranz again for a wonderful, wonderful talk. And let's have a big hand of applause.
Thank you, Roy. Thank you.
Thank you so much. I want to thank all of our audience, both here live and online, for your loyal support, and especially our sponsors, the Dr. Lois Tiffany Endowment, the Hideko Tamazawa Endowment, the Van Loo family for supporting outstanding university students who present public lectures at Saturday Morning Physics. I want to thank Carl Cole, our Michigan media team, Carol Raybuck, our communications director, and Monica Wood and her wonderful team in the demo lab for setting up the demonstrations that we all enjoyed today. And I want to mention that we have a very exciting program in the winter semester, starting late January or early February. One of the highlights is going to be a live session with an astronaut, a Michigan astronaut, on the International Space Station, and the location where we'll hold that is not yet fixed, and the date depends on the NASA schedule, but we'll keep you informed about that, and that'll be part of our opening SMP presentations for the new year. And we look forward to seeing you all again in the new year, and wish you all a happy holidays. Thank you very much for your attendance.
Thank you.